Okay, so looking at today's notes, we have chapter 1, section 3, and we're on day 3 of it because you had that work day yesterday. Continuity and end behavior. The last section of notes we talked about continuity. Today we're talking about end behavior. End behavior is talking about what happens on the ends of the graph. That's really the only parts we're concerned about, is the left end and the right end. For most of the problems, they fall into one of these 4 categories. Rational functions kind of have its own thing, so I'll talk about rational functions at the end. But anything that's not a rational function will fall into one of these 4 categories. So the first situation is we're going to look at the highest degree of the polynomial. If the degree is odd, like 3x to the 3rd power, 5th power, 5th, 9th, any odd number, then it will look, and its lead coefficient is positive, so we have a positive odd function. It'll look something like this, like that's a quick sketch of x to the 3rd power, right? The cubic function. All sorts of stuff could happen in the middle. There could be ups and downs, zigzags, all sorts of weird things happening in the middle depending on the actual function itself, but we're not concerned about anything that's happening in the middle. Just what's happening all the way as you go to the left, as x goes to the left, what is happening on the graph, where's y going, and as x goes to the right, what happens with y, where's y going. So the end behavior, and this is just an abbreviated quick notation. The end behavior, here I'm talking about the left end, and this is the right end. Left, right is referring to the x-axis, right? As x goes to the left and as x goes to the right. So as x goes to the left, we start from the origin. As x goes to the left, the function is going down. The y values are going down towards negative infinity. From the origin, as the x values get larger, as we move towards the right-hand side, the y values are going up towards positive infinity. So the left end behavior is negative infinity. The right end behavior is positive infinity. Your end behaviors will be an infinity unless you have a rational function. Then sometimes it is, sometimes it isn't. But we'll get to the rationals in a minute. Okay, so the next situation is still an odd degree. But if it's negative, a negative odd function means you reflect it across the x-axis. So now as you go to the left, the y goes up to positive infinity. As you go to the right, the y goes down to negative infinity. So the end behavior of odd negative is positive infinity, then negative infinity. An even function, they're going to go the same direction. You just have to figure out, are they going to point up or are they pointing down? So an even, x squared, x to the 4th, x to the 6th. If it's positive, both ends point up towards positive infinity. If your even function is negative, that means it's been reflected. So both ends point down towards negative infinity. All right. So we're going to use that information to determine end behavior. For the first example, we have f of x equals negative x to the 4th plus 8x to the 3rd plus 3x squared plus 6x minus 80. Really all we're worried about at this point, or what we need to look at, because we're only determining end behavior, is we need to look at the highest degree. And you do need to make sure you're in standard form. The book might throw one that's not in the right order, so then first you would need to reorder it. The highest degree in this one is a 4. So over to the side, I'm going to say degree. And I need to figure out the lead coefficient. So the highest degree is degree 4. 4 is even. And now I need to figure out is it positive or negative. So I look at the lead coefficient. It's a -1. So that means it's negative. So I have an even negative function. Even negative looks something like this. Anything could happen in the middle, but they're both ends are pointing down towards negative infinity. So I'm going to do a here. So I know it's going to look something like that because it's even negative. Then I'm going to write it in limit notation. So the limit as x goes to negative infinity of f of x equals, I'm going to go ahead and set it up before I answer anything. And the limit as x goes to positive infinity of f of x equals. So if I'm going to write end behavior, this part doesn't change. I mean, if you had g of x, obviously that would change to g of x or h of x or whatever your function's name is. This one is an f function. So limit as x goes to negative infinity. That just means the left end behavior. So this is just referring to left end behavior. What's happening as you move towards the left? And this limit as x goes to positive infinity is telling us from the origin we're moving to the right side. Right end behavior. So this part will be the same for all of your functions. You're going to tell me what's going on the left side as x moves towards negative infinity from the origin and as x moves towards positive infinity from the origin. What it's equal to is what is y doing as x moves. Yes.
So no matter the function will always be a negative and a positive infinity.
Because this is x is going to the left, x is going to the right. So from the origin, it's saying we're going to move to the left. So it's talking about the left side and the right side. It's as x moves. That's what this is saying. As x moves to the negative and as x moves to the positive. So as x moves left and x moves right. So if we come over here to our quick sketch, since this is even negative from the origin, as we go to the left, as x moves to the left, y is going down to negative infinity. As x moves to the right, y is going down to negative infinity. The even functions, they will be the same. But that is how I'm going to have you write your end behavior in limit notation. Another example, f of x equals x to the third power minus 9x squared plus 2. Again, determine the end behavior. I could, just to not get confused, before I start even working with the problem, if I know I'm writing end behavior, I can go ahead and set it up. The limit as x goes to negative infinity of the function f of x equals, that's my left side, and then limit as x goes to positive infinity of f of x equals. So that's just the format for my answer. Talk about the left side and the right side. So then to figure out what they are, where they're going, I'm going to look at the degree and the lead coefficient. Lead coefficient. So the highest degree of this function is a degree 3. 3 is an odd number. So then I need to see, is it positive or negative? So I look at what's happening as my coefficient in front of x. There's nothing there. So if there's nothing there, that's an understood 1, right? It's that invisible 1. That is positive. So I have odd positive. That is up to the right. So it looks like that. If I want to, it might help, I don't know, to your sketch, say that this, since it's pointing down, is pointing to negative infinity. Since it's pointing up, it's pointing to positive infinity. If that helps you map it out that way, then do that. So now I'm ready for my answer. The limit as x moves to the left, well, from the origin, when I move to the left, the y is going down to negative infinity. And then the limit as x moves to the right, from the origin, as I go to the right, the y is going up to positive infinity. So the end behavior will be either negative or positive infinity most of the time. Okay? So then we have that the rest of the time when it's not a positive or negative. So rational functions can be tricky. This one's going to be a g of x. Same instructions, determine the end behavior. G of x equals, we have negative 24 over x. So this doesn't match one of our 4 situations from up above because that's a rational function. Rational functions are a little different. They could still have end behavior as either positive or negative infinity. That's a possibility. But they could also have horizontal asymptotes. So you have to remember the rules from Algebra 2 of dealing with horizontal asymptotes to check to see if it has one. If it has a horizontal asymptote, that will be the left and the right end behavior. If it doesn't have a horizontal asymptote, then you'll have to see, is it a positive or negative infinity? So, the rules of rational functions for horizontal asymptotes say you compare the degree of the numerator with the degree of the denominator. Here I have a degree of the numerator. There's not an x in the numerator. So if there's not an x in the numerator, I can put one up there and say it's a degree 0, because anything raised to the 0 power is just 1, right? So if there's not a variable in the numerator, it's because it has a power 0. In the denominator, we have x, so that's x to the first power. And like I said, we're comparing the degree of the numerator with the degree of the denominator. So we want the degree of the numerator, I'm going to call it n, is 0. The degree of the denominator, I'm going to call that d. That's 1. So degree of the numerator is 0. Degree of the denominator is 1. The degree of the numerator is less than the degree of the denominator. N is less than d, because 0 is less than 1. If the degree of the numerator is less than the degree of the denominator, then you have a horizontal asymptote at y equals 0. Okay, so if I were to sketch that, I need to just to be clear what I'm talking about, HA is horizontal asymptote. So if I do a quick sketch, this is negative 24. So I know the original parent rational function, 1 over x, is kind of sort of like this. Right? Looks something like that. That's f of x equals 1 over x. That's the parent function. But this one is negative. So that means I have it flipped. So it's going to be like this. This is g of x. And I have this horizontal asymptote at y equals 0. Here's 0. So I can see also from the origin, if I follow the graph to the left, that means I have to jump over here to the graph bit that's on the left side of the y-axis. And as I move to the left, I start by going down towards negative infinity, but then it just kind of goes to the side because there's this basically roadblock. This asymptote serves as sort of a detour roadblock. I can't keep going down. I have to kind of go over to the side, and then it just becomes horizontal. So that's my limit. My limit is that asymptote. So as I move to the left, I have a limit at 0. I can check it on the right-hand side. From the origin, I move to the portion of the graph on the right-hand side of the y-axis. And I start following it as my x values are getting larger. My y starts getting larger, and then it starts going horizontal. And because it has that same roadblock or limit at 0. So the limit, again, I can set it up. If you find it confusing, you can set it up every time. The limit as x goes to negative infinity, so the limit as you move to the left of g of x equals, and then do the other side, the limit as x moves to infinity, as x goes to the positive infinity of g of x. So I set up the left side and then I set up the right side. They both have a limit of 0 because at 0 it starts going flat. It doesn't go down anymore. So 0 and 0. Not every rational function has a horizontal asymptote. Sometimes the limits of your rational functions will be positive or negative infinity. You have to follow the asymptote rules. Yes.
So if the numerator is less than the denominator, then the asymptote is whatever the denominator number was. Or is it just 0?
It's 0.
Always 0.
If the numerator is less than the denominator, the horizontal asymptote is at 0.
And if it's not, then it's
If they're equal, then it's the ratio of the lead coefficients. And if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote.
What do you mean by the ratio of the...
In this case, negative 24 over 1 would be the lead coefficients. Negative 24 over 1, because that one's a 1, and so it would be negative 24.
So it would just be like you just divide or solve whatever those two are.
Mm-hmm.
And that'll be the asymptote.
Yes, I'm going to put up my notes on that. My Algebra 2 rational function little note card I have. Your assignment is page 30. We're going to do numbers 23 to 29, number 33, number 39, and number 43. I want you to do at least 1 or 2 of them today because I understand it can be a little confusing when you first start. And we're going to work on this tomorrow also.